EE World, I'm Martin Rowe. We're at the 6G Symposium in Washington, D.C. And we have a demonstration here from Bob Stevens at Keysight. So Bob, why don't you tell us what you've got going here and how it relates to 6G?
Okay, so what we have here is we're demonstrating an ORAN network. Now this is a 5G ORAN network, but for a lot of the story problems that 6G is trying to solve, I'm going to show you why you need to have this as a starting point and how you can solve some of those 6G problems and prototype them in an environment like this. So just to start, what we've got here is we've got a completely virtualized network. This is showing a virtual G-Node B that's a combination of this SRS RAN software that's virtualized running on a Dell server over here. And also we have our 5G core network here running on a Dell server that's on that same Dell server box. So everything in yellow is running on the same server.
Okay.
And so what we have, we're doing that by running virtual machines. So we have here this agents and licensing VM and MDW. These three together these three virtual machines make up the simulated 5G core. Then we're simulating SRS RAN here in a separate virtual machine, which has got the DU and the CU from ORAN. Now, go ahead.
Okay, and just for our readers who don't know, what Bob's talking about is the disaggregating of the radio, which is shown over here, the ORU, and the distributed unit, and the centralized unit, which traditionally have been in one box.
That's right.
And with an open radio access network, we're separating those and having standardized interfaces in between them.
Exactly.
Okay, so go ahead, Bob.
Right. Yeah. And so, okay, so now, we've got this network running here. And so next thing I'm going to show here is I'm going to start up the network here. So what I'm going to do is I'm going to go here. So this is that RU-SYM that you saw. That RU-SYM actually simulates both the radio unit and the UEs. And so what you're seeing here is the GUI is showing us that there's no signal. So that says that the UEs that are sitting out there aren't seeing any signal from the base station yet, from the G-Node B. So now what I'll do is I'll go here and I'm going to start on that virtual machine, that SRS RAN virtual machine. I'm going to start the G-Node B up. And so, okay, and so there it goes, and it's starting up. And core duct. Uh-oh, that wasn't good. What happened there? Usually that doesn't happen. Let me try that again here. Okay. Oh, no. Oh, I'm sorry. That's a good demonstration. I forgot something. This is supposed to happen.
Okay.
So what happened
what
happened was the reason the core dumped there was because we didn't start the core network. So let's go start the core 5G core network.
Okay. So we got an error flag there.
There we go.
Okay.
All right. So so now we're starting the core network, and as soon as this is started up, again, that's in one of the other virtual machines. Okay, so now the core is started there. So now we'll go back and we'll see if we're successful this time in actually starting the G-Node B. Okay, that time it started. It was happier.
Okay.
And now you can go over here and you can look over here and you can see now before we had no signal, but now this says synchronized.
Yes, it does.
So this means we're synchronized to the system synchronization blocks are being transmitted on the downlink. And if we go look here, what we're able to do is in this environment we can tap off here and we can feed our WaveJudge software, which is a software that does protocol analytics from the IQ data from complex numbers all the way up to layer 4. And so we can see here, you can see there's a little SSB block, but I'll show you here in the real trace here. So you can see here that when the radio is saying it's synced, well, that's because we're actually seeing the mid here. So I'll go here, and the WaveJudge software is interesting because, just a side note of the WaveJudge software, it decodes the protocol stack, the messages, but it also decodes the layer 1 physical layer, and it's all correlated. So as you step through and look at different messages, you can look to see what complex numbers, IQ data went with each message on these things. Very interesting. Anyway, okay, so now we'll go over here and we'll go look at those SSB blocks.
Now, those constellation diagrams that you had up a moment ago,
Yeah.
are those, and you also had a waveform that was over in this part of the screen.
Yeah.
Yeah, there we go. So now, are these also synchronized to each of these messages?
They are, exactly.
They are.
Exactly.
Okay.
It's a good point. So what happens here is this SSB, this MIB, that's what's WaveJudge. When WaveJudge is decoding like a real phone and a real base station. And what it does is it watches the scheduled allocations and it draws a cartoon overlay for where something should have happened. And then what you can do is you can look at the underlying energy and see, was there energy there and how healthy was it? So here, as you noted, that we see the constellation here, healthy QPSK, pin dots. We also in the frequency domain see a nice crisp allocation in the frequency domain here for that allocation. And you will also note here that the PLMN is shown here for the decode on the downlink. These are this is the signature of the Geno B to say, you know, what manufacturers, what country, and all that stuff. Now, what we'll do is we'll zoom in a little bit on this MIB here, and if we zoom in, you can see here that we can look at this and see what all these pieces are. So we can look here and we can see that's a DMRS, demodulation reference symbol, and we can see what the power is. We can look over here and see that's primary sync channel, and then we can go in the middle here and see that's secondary sync channel. So that's what makes up the SSB, and we're decoding that from this downlink, and we're able to sniff that using WaveJudge because of the disaggregated interface here at the front hall. We're able to take a look at that and see what's going on here for what's happening.
Okay, very good. Thank you.